Hi, my name is Matthew Russo, and today I'll be presenting work on Inquest, which is a system for accelerating aggregation queries over unstructured streams of data. I'll be presenting this work on behalf of myself, as well as Professors Tatsunori Hashimoto, Daniel Kang, Yi Sun, and Mateza Haria. With the proliferation of edge devices, such as video cameras and smartphones, we're increasingly capturing streams of video, audio, and text. And with this increased data capture, there's a unique opportunity to solve challenging real-world problems by executing queries over streams that produce results in real time. For example, firefighters might be interested in executing queries over a set of video feeds to identify the location of fire starts. Ornithologists may want to query for bird songs to populate a dashboard showing bird populations in a given forest. And tech writers may want to query Twitter to create a live leaderboard showing sentiment around different large language models. Before diving deep into the presentation, I want to distinguish between two different scenarios for query processing on streams. In the first scenario, the stream is uploaded to storage during ingest time. Then, after the stream has been partially or fully uploaded, queries are executed at query time. I'll refer to this scenario as the batch setting. In the second scenario, the stream is processed on the fly without the need for buffering or storage, and query results are generated in real time. I'll refer to this as the stream setting. Unfortunately, systems designed to operate in the batch setting are not well suited to answering queries in the stream setting, where results need to be generated in real time. For example, consider two such systems, Tahoma and Abe, which execute aggregation queries with predicates in the batch setting. Tahoma samples frames from the ingested dataset to train a set of model cascades, which it then can use during query execution to answer user queries. The problem here is that training the model cascades can take up to 12 hours. Similarly, before it can answer a user query, Abe must pre-process the entire dataset by running a small neural network known as a proxy model on every frame of the dataset. Fundamentally, these pre-processing steps prevent these systems from producing inquiry results in real time, which makes these systems incompatible with the stream setting. On the other hand, systems such as video monitoring queries are capable of providing results in real time and are designed to operate in the stream setting. However, these systems are typically specialized or have specific architectures for a single data modality, and therefore cannot be used to process streams of other modalities such as audio or text. As a result, we set out to design a system we call Inquest to address this problem. Specifically, we designed Inquest to accelerate streaming aggregation queries with or without predicates, while providing statistical guarantees on query estimates and being able to process multiple modalities of data. To understand how such a system might work, consider a simple approach that uses uniform sampling. We would expect the system to accept three inputs: a stream, an accurate but expensive to execute deep neural network, which we call an oracle, and an aggregation query. In this example, which I'll use throughout the talk, our query computes the per frame average number of votes from a video stream. And it also contains a predicate which filters for frames with at least one vote. As is common in the approximate query literature, it also accepts an integer value known as a budget, which specifies an upper bound on the number of times the oracle may be invoked on records on the incoming stream. This is typically a way of limiting the execution of the oracle subject to users' resource constraints. To actually execute the query, we first sample frames uniformly at random from the stream in accordance with our sampling budget. We then run the oracle on each of the sampled frames to compute our statistic of interest, in this case, the count of votes. We then filter out any records which do not satisfy our predicate before finally computing our query estimate on the predicate matching frames. And while this approach works, we can see that it will break down or fail to produce good results on queries with highly selective predicates, because uniform sampling will naturally fail to sample lots of predicate matching frames. So a natural question to ask is, how can we do better? One technique which has been used in other papers in the approximate query processing literature is to use what I'll call here as the proxy method. In this setup, the user also provides a very cheap to execute model known as a very cheap to execute neural network, which is called a proxy model. And this model typically does something like computing an estimate per frame that a given frame satisfies the predicate. Using these proxy estimates, we can then better inform our sampling decisions when we pull records from the stream. So to see how this would work, let's consider the same example as before, but this time we expect the user also to provide their cheap to execute proxy model. This model then is run on every single record in the stream in real time and produces probabilities that each frame satisfies the predicate, which I show above the records. According to some logic, we then use these probabilities to decide which records to sample from the stream, and we pass them on to our oracle as before to compute our statistic of interest. This time we find that each of the records that we sampled satisfies our predicate, and so we compute what we expect to be a higher fidelity query estimate on the predicate matching frames. So this technique works, but one key detail that I've left out is how exactly we should leverage these proxy estimates to choose which records to sample from the stream. For Inquest, we ultimately decided to use a technique known as stratified sampling. We chose this for two primary reasons. First, stratified sampling is provably more accurate than uniform sampling, given a fixed sampling budget. And second, stratified sampling provides standard frequentist bounds on its estimates out of the box. To understand how stratified sampling works at a very high level, consider the following toy example. On the left, we have a stream that has it's been annotated with proxy probabilities above and below the records. As a first step, we choose some proxy thresholds, which we use to stratify the stream into individual stratum, or you could think of it as buckets. Once we've stratified the stream, we then apply our sampling budget under some allocation across each strata and draw samples individually within each stratum. Finally, we compute our query estimate as a weighted mean of the per stratum averages. Now, while this technique is good in theory, implementing it in practice, particularly in the stream setting, is much more difficult, or I should say it's much easier said than done. And to understand why this is so difficult, consider the following three challenges. First, we don't know ahead of time what the distribution of proxy scores is going to be in our stream. And so this makes it very difficult to choose an optimal setting of our proxy thresholds to create our different strata. Assuming that we've done that, we then have to choose how should we actually allocate our sample budget across these strata. From the theory section of our paper, we show that there is an allocation which can minimize the variance of our query estimates. However, computing this optimal allocation requires knowing the ground truth per stratum standard deviations and predicate match rates, which we can't possibly know unless we were to run the oracle on every record in the stream. Finally, after solving these first two issues, we still have to actually sample records from the stream in an unbiased manner. To understand why this is difficult, consider the naive greedy approach, where we sample the first K records within each stratum that just sample the first K records within each stratum such that those records fall into the stratum. This would produce a sample that exhausts our sampling budget, but it would be heavily biased towards the beginning of the stream. Instead, what we want to do is we want to produce a sample that is uniform in time within each stratum, but without knowing ahead of time how many records are actually going to fall into those strata. Overcoming these three challenges largely guides the intuition behind our design of Inquest. On the right-hand side, I show a system diagram illustrating Inquest's design, which I'm going to walk through step by step using the working example on the left. For starters, it's worth mentioning that Inquest processes the stream as a series of non-overlapping tumbling windows of fixed length. For the first step, Inquest uses a technique known as pilot sampling to compute initial estimates of key quantities. Specifically, it computes an initial estimate of the proxy thresholds that stratify our stream, as well as an initial estimate of the optimal allocation for our sampling budget. To compute our initial stratification, we take each record in the first tumbling window and find the stratification that evenly divides those proxy values. We then, only for the first tumbling window, use uniform sampling to draw records from the stream. And given the Oracle outputs on these records, we compute an initial estimate of the optimal sample allocation. For each subsequent window, we then use a technique that's known as reservoir sampling in order to draw samples from the stream for each stratum that are uniformly spaced in time. And I don't have time to go into the specifics of reservoir sampling in this talk, so please refer to our paper for more details. At the end of each tumbling window, we then use a weighted average of the history of the samples that we draw to update our stream stratification, as well as our computation of the optimal sample allocation. And finally, at any point in time, users can grab the latest query result from Inquest. So in order to evaluate our algorithm, we used 6 real-world video and text datasets. The video datasets were shot using fixed-angle cameras of traffic intersections and canals, and our text dataset consisted of a series of tweets between customers and customer support accounts on Twitter. For each dataset, we executed 2 sets of queries, one with a predicate and one without. For the video datasets, these queries computed the per frame average count of cars or boats, depending on the dataset. And when we used a predicate, we filtered for frames that had at least one car or at least one boat. For our text dataset, we computed the average sentiment of the tweets. And for our query with predicate, we filtered for tweets that came from customers. Our evaluation metric was the the per window median root mean squared error. And so to compute this, what we did was we had Inquest and our baselines compute a query estimate for each tumbling window. We then computed the root mean squared error for these windows by referencing the ground truth statistic. And then finally, we took the median of these per window values. We evaluated Inquest against 2 streaming baselines. The first one was uniform sampling, which I introduced earlier in this talk. And the second was stratified sampling, where we fixed the proxy thresholds as well as the per strata sample allocation using a naive prior. We also evaluated Inquest against ABAY, which was a state-of-the-art algorithm from the batch setting. Now, you may recall that I said earlier that batch algorithms cannot produce results in the stream setting, and this is true. To perform this evaluation, what we did was we ran ABAY on each dataset in the batch setting, and then we simulated what its query estimates would have been had it chosen the samples that it chose in a streaming fashion. So in this sense, ABAY has a slight advantage in this evaluation framework. What we find is that Inquest consistently outperforms our baselines and ABAY across all 6 evaluation datasets. On the right-hand side for our Night Street dataset, which is one of our video datasets, we plot the per window median root mean squared error as a function of the sample budget for 10 different sampling budgets. Inquest is plotted here in orange, and lower on the plot is better. We ran each algorithm for 1,000 trials and plot them, show the plot lines here with a 95% confidence interval. What we find is that Inquest outperforms the streaming baselines across all data sets and budgets that we considered, and it outperforms ABAY on 90% of such budgets. We also find that Inquest can achieve the same error with up to 4.5 to 5 times fewer samples than our baselines, or equivalently, it can achieve on average 1.3 to 2 times lower error at fixed sampling budget. And this just shows the performance across all 6 data sets, where the key takeaway here is that Inquest is consistently the lowest plot line on these plots. We also proved some nice theoretical properties related to Inquest, where this theory was performed assuming that the streams were stationary. In other words, we assumed that for these streams, the per stratum standard deviations and predicate match rates remain fixed throughout time. And we showed that on such streams, Inquest's will converge to the optimal sample allocation at a rate inversely proportional to the sampling budget and the number of tumbling windows, and that its error will converge to 0 at a rate inversely proportional to the sampling budget. Now, of course, in the real world and on real streams, you're not going to have these nice assumptions about stationarity. Streams are going to change somewhat dynamically. So in order to stress test our inquest, what we did was we generated 100 synthetic streams in an adversarial fashion, where at 1 to 5 random points in the stream, we injected sudden shifts in the stream parameters, namely these standard deviations and predicate match rates, and then ran each of our baseline algorithms as well as inquest on these synthetic streams. We show our results in the plot on the right. In this plot, inquest is the solid blue line at the bottom. And what we find is that inquest outperforms our streaming baselines by an average of 1.1 to 1.4x. And it also performs within 0.99 to 1.03x of A-Bay. And this is a surprising and good result when you consider that A-Bay has a considerable advantage here in that it can see the full proxy distribution for these synthetic data sets ahead of time. So it can basically take these shifts into account, whereas inquest is responding to them on the fly. So in conclusion, real-world problems are driving a demand for the ability to efficiently execute queries over unstructured streams while producing results in real time. Unfortunately, existing systems aren't well suited for the stream setting, or they can only process a single modality of data. By adapting stratified sampling to work in the stream setting, we were able to design inquest to overcome these challenges. And because inquest is modality agnostic, we believe it can be applied to a variety of real-world problems.